Okay, so good morning to one and all. In the previous lecture of electrical machine first, we have discussed regarding point is that the transformer on load condition. Okay, transformer on load condition. Also, in that I have shown the diagram related to that, and I have discussed related to transformer on load condition. So in case of transformer on load condition, that means the secondary of the transformer it is loaded. Transformer ची secondary load केली जाईल. If the secondary of the transformer it can be loaded, then the secondary current it will be start from flowing. Now due to that secondary current, due to that secondary value of current, it will induces EMF in the secondary winding. That means it will induces EMF. Also it will produces a flux phi 2, it is in the secondary winding. Now due to that flux, this produced flux it is in the opposite direction to that of flux produced at no load current or flux produced by current I0. I0 current ना जो काय प्रोड्यूस झालेला फ्लक्स आहे त्याच्या अपोजिट डिरेक्शन न phi 2 हा फ्लक्स काय होतो प्रोड्यूस होतो. So if the phi 2 it will be traveling in the iron core opposite to that of main flux phi, then the resultant value of flux it can be decreases. If the resultant value of flux it is decreases, the induced EMF at the primary coil it will be decreases. त्याच्यामुळे induced EMF at the primary coil काय होतील decrease होतील. So if the induced EMF of the primary winding it will be decreases, but the supply remains constant. To meet this value V into I as well as the power it will be constant here. So it will take an additional amount of current from the primary. It will take additional amount of current in the primary for the from the primary. This current it can be represented by I2 dash. तो जो काय current आहे तो आपण I2 dash ने represent करतोय. See here in this figure, here it is I0 current is there. Another one current is nothing but I2 dash. So due to that flux and V1 it goes an upper hand to that of induced EMF E1, so that to neutralize the effect there are additional current taken from the primary side. Primary side करून additional current घेतला जाईल. So this current we are representing here I2 dash. Okay, now when the I2 dash it will be traveling from, or I2 dash it will be flowing from that of primary winding. Primary winding मधून ज्यावेळेस I2 dash flow होईल, so due to that current it will induces a EMF or it will produces a flux in the iron core. So this flux it can be represented by phi 2 dash, but this produced flux it is in the same direction of main flux, and this phi 2 it is in the opposite direction. So additional amount of current is nothing but this current is same as that of I2. Okay, so due to that phi 2 and phi 2 dash it will be neutralizes. Phi 2 and phi 2 dash it will be neutralizes. That means phi 2 and phi 2 dash are equal, but it is in opposite direction. ते काय असतील opposite direction नसतील. Phi 2 and phi 2 dash are equal in value and opposite direction. According to this we are calculated the value of I2 dash. याच्यावरून आपण I2 dash ची value calculate केली. So MMF produced due to the phi 2, MMF produced due to the I2 current, and flux produced by phi 2. So MMF is nothing but number of turns in the secondary side into current flowing from secondary side, that is I2. It is equals to what is phi 2 dash? Phi 2 dash is nothing but this flux it will be produced by phi 2 I2 dash current flowing in the primary winding. So number of turns in the primary winding is nothing but N1, and the current flowing from that primary winding is nothing but I2 dash. Okay, so according to this we will calculate the equation, that is what is the value of I2 dash. So I2 dash it is equals to this N1 it can be shifted to the left hand side, that is N2 divided by N1, N2 divided by N1 into I2. So N2 divided by N1 is nothing but K, or the transformation ratio. So we can write this equation, that is I2 dash is equals to K into I2. I2 dash is equals to K into I2. Now when the transformer is an load condition, so primary taken supply current taken from the supply, it is nothing but it is the summation of these two current. या दोन current ची काय असेल, vector sum असेल. So see, this can be represented by I1. So we are representing that I1. I1 is equals to I2 dash, I2 dash vector sum. That means we are representing bar here, and the no load current I0 bar of that. Okay. See, again the current taken from the supply while load condition, it is the vector sum of the two current in case of transformer on load condition. And when the transformer on no load condition, the current taken from the supply, that is I0, it is again the vector sum of two component. That means component magnetizing component and the working component. That means final conclusion for that, याचं जे काय final conclusion असेल. So the transformer operation remains same. Transformer operation remains same when it is operating on no load condition or when it is operating on load condition. So this conclusion we have already concluded in the previous one lecture. Just today I have overlook on that. याच्यावरती मी फक्त overlook केले. Now we will discuss regarding the phasor diagram. How to draw the phasor diagram? While discussing transformer on load condition, I have already told that the characteristics of the transformer, it should be depends upon load attached or the load connected, which types of load connected. So when the resistive load connected, the characteristics is different. When the inductive load connected, then the characteristics is different. And when the capacitive load is there, the characteristics is different. That means output characteristics. The phase angle V2 and I2, it is depends upon the load. V2 and I2 मधला जो काय phase angle असेल, it should be depends upon load. If the V2 and I2 it is in phase with each other, that means secondary value of secondary voltage and the secondary current are in phase with each other, then we can call it as a resistive load is there. If the secondary current, it will be lags behind by voltage by some angle, that means we can call it as a inductive load. And for capacitive load, the I2 or the secondary current, it will be leads the voltage by some angle. काही angle ना काय होईल, lead करेल. Okay, so we will draw the phasor diagram one by one, and then we will discuss the losses and efficiency of the transformer. Transformer चे losses and efficiency काय करू आपण define. See, for resistive load, that means resistive load is nothing but non-inductive load. When the transformer secondary is connected to the resistive load, the current will be in phase with that of voltage. Okay, voltage and current काय असतील, in phase असतील. Okay, so we will draw the characteristics for that or the phasor diagram. See, this is the phasor diagram of that of transformer when the transformer is on load condition and the load is connected, that is resistive load. See, while drawing these characteristics, consider the phi, it is an reference phasor. Phi जी आहे ती reference phasor consider केली, that means here we can represent the phi flux. It is an reference phasor. Now the secondary value of voltage, that is secondary induced EMF, we can draw on here, that is E2. Here it is E2. Again here it is resistive load, so that I2 it is in phase with that of E2, right? See, आपण काय केलं, this phi is nothing but this phi due to that of current I current मुळेच flux phi होतोय. That means E versus V characteristics, आहे, voltage versus current characteristics. So see here, induced EMF, it can be drawn in the downward direction. Again, due to the resistive load, the current, secondary current, it is drawn in phase with that of E2. E2च्या phase मध्ये काय केलंय, draw केलंय. Now the initial current I0, initial current, that is no load current I0, it will be drawn like this. हा जो काय I0 current असेल, so this I0 current, it is in lagging phase angle. We have already tell that it is in the lagging angle, or it will lags by voltage by some of the angle. Voltage जे आहे ते primary voltage V1 आहे, याला हा काहीतरी angle न काय होतो लॅग होतो. सपोज इट विल बी लॅगिंग बाय अँगल 50. 50 अँगल ना हा काय आहे, लॅगिंग आहे. सो हाऊ टू ड्रॉ द कॅरेक्टरिस्टिक्स आय विल टेल. सी, कन्सिडर फाय विथ रेफरन्स फेजर. त्याच्यामधला फ्लक्स फाय जो आहे तो रेफरन्स फेजर कन्सिडर केलाय. नाउ the secondary voltage and the secondary current, that is secondary induced voltage and the secondary current are in phase with each other because of the resistive load. Secondary side ला load कोणता आहे, resistive load आहे. Okay, now the E2 and I2 it is in phase with each other. E2 and I2 काय आहे, these two are the are in phase with that of each other. Now we want to calculate the primary current, value of primary current and the phase angle between voltage and current in the primary. So for driving that, the voltage, that is supply primary voltage, and the no load primary current, that is no load primary current, it will be lags behind by that supply voltage V1 by and sum of the angle. It is not lag exact 90 degree. I have tell already this one. So it will lag angle somewhat less than that of 90 degree. 90 degree पेक्षा less angle ni काय होईल, lag will. So that we can represented here 50 angle. Now do you know that according to previous one relation, that is the primary current taken from the supply, third diagram मध्ये होतं बघा, that is I1, it is equals to vector sum of I2 dash plus I0. I2 dash plus I0. What is I2 dash? I2 dash is nothing but it is the additional amount of current taken from the primary, but it is opposite in direction to that of previous one I2. I2 च्या काय असेल, opposite असेल. So that the I2 it can be extended in the opposite side. So we can represented this is I2 dash. हा जो काय आहे तो I2 dash काय केला आपण, represent केला. Now the vector sum of this I2 dash and I0 it is nothing but I1. So I am drawing the parallelogram here. जर parallelogram draw केला, so if we are drawing the parallelogram here, that is vector sum, and we can connect the resultant vector, or we can find out the resultant vector here, that is this resultant value, it is nothing but the primary current taken from the supply when the transformer is at load condition and the load is connected, that is resistive load, having an, it will lags behind by primary voltage at an some angle. So this angle we can represent that the angle phi 1. Okay, so this is the phasor diagram for resistive load. This one is the phasor diagram for resistive load. Getting लक्षात आली का phasor diagram कशी draw केली मी, how it can be drawn and how it will be explained, हे लक्षात आलं का? Hello, give me reply immediately. All of you getting? Hello. I think no one is present. Give me reply immediately. Is there any doubt in this phasor diagram?
No, sir.
Okay. See, so this phasor diagram, it is for resistive load. So similar phasor diagram, it can be drawn for the inductive load and the capacitive load. See, when the inductive load, it can be connected on the secondary of the transformer. So at that condition, when the load, it can be connected inductive load, that means secondary of the transformer, it is connected to inductive load. So current, it will be lags with respect to that of voltage by an angle, sum of the angle, this angle it is less than that of 90 degree. Okay, so lagging angle, that means the secondary current I2, it will be lags behind by E2 by some angle, काहीतरी angle ना काही will lag will. So the phasor diagram for that We will draw that phasor diagram. See, the consider the reference phasor, that is flux, it is the reference phasor, and E2 it will be lags behind by that of phi exact 90 degree, that is E2. Again, the secondary current, it will lag behind by secondary voltage, that is I2, it will be lag behind by E2 by some angle. See, I am drawing here the lagging angle E2 here. Okay, so that is I2, it will be lagged behind by E2 by angle. We are representing here angle, it is nothing but phi 2. Phi 2 angle ni काय होतोय, lag होतोय. Okay, so current it will be lags behind by E2 by some angle, it is nothing but phi 2 angle. It is due to the inductive load. Okay, now again other procedure is similar, that is this is the supply voltage or the primary voltage V1, and do you know that the no load characteristics, according to the no load characteristics, the no load current, it is lagging behind by the supply voltage V1, angle not exactly less than 90 degree, sorry, not exactly 90 degree, but it is less than that of 90 degree. So I am drawing here the I0, that is no load current, it will be a lag behind by voltage V1 by angle phi 0. Okay, so this is the no load angle. Now according to the previous discussion, that is supply current or the primary current taken from the supply, it is the vector sum of the current I2 dash, that means additional current taken from the supply I2 dash plus no load current. What is I2? It is the vector sum of I1 is the vector sum of I2 dash plus I0. What is I2? I2 dash. So it is I2 dash is nothing but additional current taken from the supply. It is the additional current taken from the supply. Additional current taken from the supply, that is I2 dash, and it will produces or to neutralize the effect of flux produced by current I2, and it is I2 dash, it is equals to K into I2. K into I2 is nothing but transformation ratio K into the secondary current I2. See, so but it is in opposite direction, so we can extend this I2 dash in the opposite direction. आपण हा x2 जो आहे तो opposite direction ला extend करतोय, so it will be like this. So it is I2 dash. Okay, so I2 dash is here. Now we draw the parallelogram and we find out the resultant vector, that is, so this resultant vector is nothing but primary current I1. Okay, primary current I1, it will be lag behind by supply voltage V1 by an angle phi 1. Okay, by an angle phi 1. See, this is the phasor diagram related to inductive load of the transformer. When the transformer it is loaded, or the secondary of the transformer it is loaded, and the load on the transformer it is inductive load, then this phasor diagram it will be drawn, it will be like this. Okay, again for the capacitive load, so similar procedure is that, similarly when the transformer secondary is connected to a capacitive load, so the current, that is secondary current I2, it will be leads by some angle with V2. Okay, it will lead the respective voltage as shown in this figure. See, again the procedure is same. Consider a flux phi, it is an reference phasor. E2 it is an perpendicular to that of flux phi, here it is E2. Then the I2, that is secondary current, it will be leads with respect to that of voltage E2 by an angle phi 2. Phi 2 ना काय होते, lead होते. Okay, again the no load primary current and primary supply voltage V1, no load primary current, it will be lags behind by V1 angle not exactly equal to 90 degree, but it is less than that of 90 degree. Less than 90 degree. So see, when it will be lag less than 90 degree, so the angle between that is nothing but here represented the angle, it is nothing but 50. हा 50 angle काय केले represent केले. See, here it is angle between the supply voltage and the no load current I0, it is 50. हा 50 angle असेल. Now we want to calculate the primary current I1, and this primary current I1, it is the vector sum of I0, that is no load current I0, and the additional current taken from the supply, that is I2 dash. So I2 dash is nothing but it is opposite to that of I2 or opposite to that of secondary current. So we extend this I2 in the opposite direction like extend kela. So it will be like this. Here it is I2 dash. After that, I1 is the vector sum of I2 dash plus I0. So we drawn the parallelogram. If parallelogram is drawn, then the resultant vector I1 it can be obtained. Okay. So resultant vector I1 it can be obtained, and the this I1 it will be lag behind by supply voltage V1 by angle. So this angle is nothing but phi 1 angle. So this phasor diagram for capacitive load. Okay. So see, for resistive load, for inductive load, and for capacitive load. So the nature of characteristics, it will be depends upon load, which types of load it can be connected on the secondary of the transformer. So if the resistive load is connected, the phasor diagram it will be like this. If the inductive load is connected, then the phasor diagram it will be like this, and the capacitive load is there, then the phasor diagram it will be like this. Okay. Okay. Getting? Okay. Getting? No? Is there any doubt? We have already discussed this one in the previous lecture. Also transformer on load condition, this will be we have already discussed in the previous one. So today we will discuss the next one point, that is losses and efficiency. Before that, tell me, is there any doubt how to draw the phasor diagram? Give me reply. Are you present? No? Otherwise, I will put directly absent all. Hello, Vikas. Hello. Is there any doubt? Give me reply immediately.
No, sir.
Okay. So we will start next. See, Okay, see, the next one point is that losses and efficiency, that is losses in transformer and the efficiency. So traditional efficiency, commercial efficiency, as well as the all day efficiency. So in the transformer, in any electrical machine, the loss, it can be defined by it is the difference between input power and output power. Okay, so we have already calculated the losses and efficiency in case of DC machine, that is in case of DC generator and DC motor. We have solved some problem related to that also. Okay, so loss, it can be defined as there is some difference between the input power and output power. So do you know that an electrical transformer, it is a static device, whether there is a mechanical losses is present or not, because it is static device, whether there is present or not?
No, sir.
Okay, so it is static device, so that the mechanical losses, it will not present, like windage and frictional losses are absent. So windage and frictional losses are present in case of DC machine, that is DC generator and motor, because there are some of the rotating part is there, so there are frictional and windage losses is present, or the rotational losses we can call it as. Okay, so the transformer, it is a static device, so there are the mechanical losses, or it may be rotational losses are absent. So the transformer, it will only consist of two types of losses, that is iron loss and the copper loss. So iron loss, it will be also called it as a constant losses, and copper losses, it is nothing but variable losses. Okay, so this one we have already discussed, that is copper losses, it will be depends upon current. So as per the current variation, the losses of the transformer, it will also vary, and the iron losses of the machine, it is constant, that is transformer iron losses is constant, and copper losses, we can call it as a variable losses also. Okay, now the transformer losses, it is similar to that of DC machine, except that the transformer, it is static device, so that it is not having a mechanical losses. So see, we will discuss one by one the losses. The core losses, or it is called as iron losses. So in case of core losses, these core losses and iron losses, in that there are two types of losses, is that the ED current loss and the hysteresis loss. So this ED current and hysteresis loss, it will be depends upon the magnetic properties of the material which is used for the construction of core. म्हणजे जे काही कोर कन्स्ट्रक्ट करतोय आपण, while constructing the core, which material is used and what are their magnetic properties, whether the reluctance of that material, it is less or it may be greater, whether the permeability of that material, it is great or it may be less. So that means depends upon the material used, the losses, it will be present, that is iron and core loss. So that means iron core, or it may be ED current loss as well as hysteresis losses. Okay, so hence these losses are known as core losses or the iron losses. Okay, why it is called as core losses? That means while constructing the core, which material is used and what are the properties of that magnetic properties of that material depends upon that, or the losses, it will be depends upon that, so that we can call it as a core loss or the iron loss. Okay, so in core loss, there are ED current loss and hysteresis loss. So I have already told that the ED current loss, it can be reduces when the lamination used to that of core, that means core lamination, it is an thin, then the ED current loss is minimum. Okay, for the thick lamination is used, then the ED current loss, obviously it will be increases. Okay, see, the ED current loss and iron loss, it will be depends upon that magnetic property of the material, core material च्या magnetic property वरती depend राहील. So in that, the hysteresis loss of the transformer, we will discuss hysteresis loss, after that ED current loss. So hysteresis loss, this loss, it is due to the reversal of magnetization in the transformer core. Okay, So this loss, that is hysteresis loss, it will be present in the transformer due to reversal of magnetization in the transformer core. Okay, so I think you people already studied the BH curve, that is density BH curve, strength and density, flux density BH curve already studied. So there is a reversal in the magnetization characteristics. Due to this reversal of the magnetization, the hysteresis loss it will be occur. Okay, so hysteresis loss is due to the reversal of magnetization in the transformer core. Now this loss it will be depends upon the volume and grade of the iron used. So that means it should be depends upon the material property, material magnetic property, that means the grade of that iron which is used for construction of core, or it may be volume of that iron. So it should be depends upon that. Now also it will be depends upon frequency of magnetic reversal, that means the frequency, we can generally take it as a supply frequency F, that is frequency of the magnetic reversal, and the value of flux density, value of flux density, that is Bmax. So maximum value of flux density, so that it can be given by Steinmetz formula, that is hysteresis loss. It can be given by the one formula म्हणून hysteresis loss आपण define करतो, that is WH, it is equals to WH is equals to eta, that is Steinmetz hysteresis constant. Then Bmax is nothing but value of flux density, Bmax raised to power 1.6, Bmax raised to power 1.6 into F is the frequency, that is frequency of magnetic reversal, and the V it is nothing but volume of iron core. Okay, V volume of iron core, it is in the meter cube. See, the hysteresis loss it will be depends upon, or it is due to the reversal of magnetization in the transformer core. So this loss it is depends upon the volume of the iron core used, or the grade of iron core is used. Then the frequency of magnetization, magnetic reversal ची frequency. Also it should be depends upon value of flux density ची value वरती depends असेल. So according to the Steinmetz formula, the loss value, that is WH, hysteresis loss, it can be represented by one formula, that is eta, it is nothing but Steinmetz hysteresis constant. Eta जो आहे तो Steinmetz hysteresis constant is there. Bmax is nothing but flux density raised to power 1.6, flux density raised to power 1.6 into F into V. F is nothing but frequency of magnetic reversal, and the V is nothing but volume of the iron, it is in the meter cube. Okay, how much amount of, or how much volume iron core it can be used, what is the grade of that iron core, what is the frequency of magnetic reversal, and what is the value of flux density, depends on that parameter the hysteresis loss it will be depends. Okay, see, you know that this parameter it is based on the magnetic property of material, त्या मटेरियलच्या प्रॉपर्टी वरती डिपेंड्स आहेत. So see, once the material it can be finalized, then their magnetic property remains constant, so that we can call it as a constant loss. त्याच्यामुळे आपण याला constant loss म्हणतोय, because it should be depends upon the magnetic property of material. मटेरियलच्या magnetic property वरती काय असतील, depends असतील. So magnetic property in that, how much volume iron material, core material is used, what is the grade of that material, the frequency of magnetic reversal, as well as flux density of that material. Okay, so according to this Steinmetz formula, the formula of hysteresis loss is becomes WH is equals to eta into Bmax raised to power 1.6 into F into V. Okay, where eta is nothing but Steinmetz hysteresis constant, then Bmax is nothing but flux density raised to power 1.6. all of you write this formula, because it is important while solving a problem. and some of the gate question is also asked in from that formula. And the F is nothing but frequency of magnetic reversal, म्हणजे जे magnetic reversal मुळे losses होते. So according to BH curve, how much reversal it can be happen. So it is depends upon the frequency of that reversal, magnetic reversal frequency. And the V is nothing but value of V is nothing but volume of iron core volume. Okay, so according to this formula it will be get. Okay, now second one type of loss, or second one loss, it will becomes under the iron and core loss is nothing but ED current loss. Second one loss is nothing but ED current loss. So ED current loss, that is ED current loss is nothing but in a transformer and current is supplied to the primary winding which set up a alternating magnetic flux. So we have already studied the transformer on no load condition. आपण no load condition चा transformer बघितलेला आहे. When the supply current is flowing from the primary winding, ज्यावेळेस primary winding मधून supply current flow होतोय, it will set up alternating magnetic flux. तो alternating magnetic flux set up करतो. When this flux, it will be links to that of secondary winding, ज्यावेळेस हे secondary winding ला link होतील according to the working principle of the transformer, that is mutual induction principle. According to the mutual induction principle, the this flux, when this link with that of secondary winding, due to that linking, according to principle, the it will produces a EMF in the secondary coil. त्याच्यामुळे secondary coil मध्ये काय होतात, EMF induce होतो. Now, but some part of this flux also gets linked with the other conducting part of the steel core. Okay, suppose see not total flux produced in the primary winding, it will links to that of secondary, म्हणजे primary winding मध्ये produce झालेला जो काय flux असेल, not total flux, it will be links to that of secondary. That means there are some of the flux linkage is there, flux leakage is there, not a linkage, flux leakage is there. So when some of the flux is leak and it will be link with the some of the other conducting part, म्हणजे do you know that core जे आहे, suppose core it is having an some other conducting part, copper material is there, so it will links to that of other conducting part like steel core, or it may be iron body of the transformer. Okay, लक्षात येते का बघा, when the primary current it will be flowing through that of primary winding, or the supply current it will be flowing through that of primary winding, at that situation it will set up some of the flux in the primary coil. त्याच्यामुळे primary किंवा पहिल्या coil मध्ये काहीतरी flux setup होईल. When the flux it will be set up in the primary coil, ज्यावेळेस primary coil मध्ये flux setup होईल, this flux it will be travel in the iron core. तो flux iron core मध्ये काय होईल, travel, and some of the flux it will be links to that of secondary coil. इथं secondary coil असेल, याच्यामध्ये काहीतरी flux काय होईल, link होईल. Not a total amount of flux produced in the primary coil. Suppose primary coil मध्ये flux phi induce झालेला आहे or produce झालेला आहे, not a total amount of flux it will be links to that of secondary coil. सगळा flux secondary coil ला link होत नाहीये. So there is a this sum of the flux it will be links to that of other conducting part of the core. जे बाकीचे जे काय conducting part असतील कोरचे त्याला लिंक होईल. That means there is a leakage of some flux. त्याच्यामध्ये leakage होतो म्हणजेच loss होतो, right? Leakage is nothing but loss. So this flux it will be links to that of other conducting part, like conducting part is nothing but steel core, or it may be iron body, or the transformer body. Okay, so transformer it is made up of a core. So core it is made up of either a steel material, or it may be iron core type core, or it may be it is the transformer other material body. So suppose this is having an somewhat conducting capacity, काहीतरी जर त्याची conducting capacity असेल, so some flux it will be links to that of conducting part. त्या conducting part ला काय होते, link होते. So which will result in induced EMF in those part. त्याच्यामुळे काय होईल, see there is a mutual induction principle is there. एका कॉइल मध्ये एक कंडक्टिंग कॉइल आहे, एका कॉइल मध्ये जो फ्लक्स प्रोड्यूस होईल तो दुसऱ्या कॉइल ला लिंक होतोय. नॉट टोटल अमाउंट ऑफ फ्लक्स इट विल बी लिंक टू दॅट ऑफ सेकंड कॉइल, some of the flux it will be linked to that of other part of the transformer चे जे काही construction part मध्ये material असेल त्याला link होईल. Due to that it will induces some of the EMF in that coil. या coil मध्ये काहीतरी EMF काय करेल तो म्हणजे या conducting part मध्ये it will induces and EMF. What will happen when the EMF it is induced in that in the core part or this conducting part? This induced EMF it will set up some of the core. It will set up some of the current. हा जो काही induced EMF असेल, it will set up some of the current, and this current it is called as circulating current. Getting? So see, when the primary coil or the first coil it will produces some of the flux. When this flux is travel into the core and when it is linked to that of secondary coil, not total amount of flux it will be links to that of secondary coil. Some amount of flux it will be links to that of some conducting part of the transformer. जे transformer चे conducting part असतील त्याला link होईल. Due to that or according to the principle, it will induces some of the EMF in that conducting part. त्या conducting part मध्ये काहीतरी EMF induce होईल. So due to that induced EMF, it will set up a small amount of current. Okay, current in that conducting part. त्या conducting part मध्ये काहीतरी amount चा current काय will produce होईल. And this current it is called as circulating current. Okay, this current it is called as circulating current, or this small amount of current causing a small circulating current, and this current it is called as ED current. Also this current it is called as ED current, and due to that ED current some of the energy it will be dissipated in the form of heat. So this dissipated energy it is nothing but ED current loss. Okay, this dissipated energy it is nothing but this is the one type of heat loss due to the ED current. So that the name given, that is ED current loss in the transformer. Okay, due to that ED current or due to the circulating current of the transformer, there is some of the energy it will be dissipated in the form of heat. So that loss it will be happen. So these types of loss it is called as ED current loss. Getting no?
Yes, sir.
Okay, so this is the again see this loss it is depends upon that conducting part. That means constructional features जे काही conducting part असतील core, either it may be steel core or it may be iron body, so that it is comes under the constant loss. Okay, and these losses, that is constant losses, it can be calculated by conducting OC test, that is open circuit test, or नो लोड टेस्ट ऑफ द ट्रान्सफॉर्मरची नो लोड टेस्ट कंडक्ट केल्यानंतर हे लॉसेस काय करू शकतो आपण कॅल्क्युलेट करू शकतो. ओके, सो वी विल सी दिस while conducting the practical related to test. Now the variable losses, that is just 1 minute. See, the variable losses, or it is nothing but copper losses. See, the copper losses in the transformer. The copper loss is due to the ohmic resistance of the transformer winding. Okay, so this is due to the resistance of the transformer winding, and the copper loss in the primary winding. Suppose the primary winding having and some of the resistance, that is the primary winding having and the resistance is nothing but R1, and the current flowing from that primary winding, suppose I1, it will be current flowing from that primary winding. So the copper loss, do you know the already you know the formula? Copper loss is nothing but the loss it will be occur in the form of heat due to the resistance of that winding, that is primary winding and secondary. So PCU it will be I square R loss, that is I1 square into R1. Okay, similarly the secondary winding having and resistance is that R2, and the current flowing from that is nothing but I2. So the secondary winding copper loss PCU it is equals to I2 square into R2. I2 square into R2. See, these copper losses, it will be occur due to the current I1 and I2. Current I1 and I2, that means current in the primary winding and current in the secondary winding. Also, it will be depends upon the resistance of the primary winding and the resistance of the secondary winding, that is R1 and I2. See, this loss it depends upon the square of the current. That means copper loss PCU, it is depends upon the current square, that is square of the current, and the current depends upon the load. Okay, so current taken from the supply as well as secondary current and primary current, it will be depends upon the load. So this loss, that is copper loss of the transformer, it will varies with the load. That means when the load varies, the current it will be varies, and when the current it will be varies, the loss it will be obviously varies, so that we can call it as a variable loss. Okay, so it should be call it as a variable loss, that is it should be vary with that of load, and when the load vary is nothing but the current it will be vary, and it is depends upon the square of the current. So PCU is directly proportional to I square. PCU, that is copper loss of the primary winding, it is equals to I1 square into R1. Then copper loss in the secondary winding is nothing but I2 square R2. So according to this, we will conclude that the copper loss, it is directly proportional to I square. If the I square changes, sorry, if the current changes, the copper loss it will be changes. So that we can call it as a variable loss of the transformer. हे ट्रान्सफॉर्मरचे काय झाले, variable loss झाले. Okay, so see, in case of the transformer there are only two types of losses, that is iron loss and copper loss. The mechanical losses is not present because it is a static device. There is no any rotational part, or it may be no any rotational mechanism, so that the rotational losses or it may be mechanical losses, it will be absent. Only two types of losses, that is iron loss and the copper loss. So iron loss, it is called as constant losses. Copper losses, it is nothing but variable losses because it will vary with the load varies. And the core losses or the constant losses, it is nothing but it will be depends upon the magnetic properties of that of material used while construction. Okay, so these are the losses in case of transformer. Okay, transformer चे losses getting.
Yes, sir.
Okay. Now the efficiency, concept of efficiency. Do you know that the efficiency it is nothing but it is the output power divided by input power. We can define that efficiency is nothing but it is the ratio of output power divided by input power. Like other electrical machine, the efficiency of the transformer, it can be defined as the power output or the output power divided by the input power. So efficiency we can represent it that the P out divided by P input. Okay, so transformer are the most highly efficient electrical device. Most of the transformer have full load efficiency, it is in between 95% to 98%. Okay, so काही transformer ची जी काही full load efficiency असेल, it is in between 95% to 98.5%. As the transformer it is having an highly efficient, that means there is a minimum loss, so output and input are nearly at the same value. Okay, so that means the losses it is minimum, and the output and input it is nearly equal to minimum. So hence it is impractical to measure the efficiency of the transformer by using the output and input. So the better method, it can be used to find the efficiency of the transformer using the formula. So do you know that the output is equals to input divided by, so see I will write here, the efficiency is equals to output divided by input, output divided by input. Do you know that the output is nothing but input minus losses, So input minus losses divided by input. Okay. So if we separate out this, input is divided by this both. So input divided by input is nothing but 1 minus losses divided by input. Okay, that is equation we can write is nothing but 1 minus losses divided by input. So according to this formula also we can able to calculate the efficiency of transformer. Okay, so this is efficiency of the transformer. It is equals to 1 minus losses divided by input. So this formula it can be used. According to this we will derive the condition for efficiency, that is condition for maximum efficiency. So this condition we will derive in the next lecture. So this is the little bit derivation. We will derive this derivation in the next lecture. Is there any doubt in this today's session? Any doubt?
No, sir.
In this way, we will conclude this today's lecture and we will stop here.